Alright, so here's an important fact about integrals, and it's that the absolute value of an integral is less than or equal to the integral of an absolute value. And the basic idea here is that integrals are very much like a special type of sum, and that's why like the integral sign looks like an S, like it was Leibniz, or I think it was Leibniz rather than Newton who came up with that sign for the integral. I forget which one of the two it was. Or it might have even been someone else, because I know the big difference between them is their derivative notation. Because I think one uses ddx and one uses f prime, but whatever. Whoever came up with the integral, it's supposed to look like an S, and the S means sum. And yeah, like we've talked about in this section, the integral is just the limit of a type of sum. So anyways, we know with sums, the absolute value of a sum is less than or equal to the sum of the absolute values. That's just the triangle inequality, and it's absolutely critical in real analysis. And so if this integral is a special type of sum, and actually I think it's actually a more general type of a sum, because really what a finite sum is you're just doing an integral over a discrete measure. But in any case, we want to prove this. So we're going to start by defining this new function, f plus, and this is going to be the maximum of f and 0. And this is sort of like, they probably should have told you to consider this. I mean, this might not be the way that you have to prove this exercise, is by writing f in this way, but this is sort of like a standard way to say things about absolute values of functions, is to define this function f plus, and then later on we'll define another function f minus, and we'll use f plus and f minus to define the absolute value. So it probably would have been nice to have a hint to look at this, because if you don't know to do this, like, how do you come up with this? I guess you could sort of come up with it on your own, but it'd be tricky. And of course, the only reason I thought to do it was because this is a standard thing that you do when you learn about Lebesgue integration, which is integration using measure theory. So if you don't have that exposure, then you might not know to do this. But anyway, so we define f plus to be this. For any partition P, I claim, what do we want to prove? We take UF plus P minus L F plus P. We want this to be less than or equal to U FP minus L FP. And why is this going to be useful? This is going to be useful because we know that one of the equivalent conditions to a function being integrable is that UFP minus LFP is, we for any epsilon there's a partition which will make that difference less than epsilon. And so if we can bound that difference for f plus in terms of that difference for f, then we can use the integrability of f to infer the integrability of f plus. So that's our idea. So to define this is sort of an odd argument that you have to make. So we take the sum over all S in our partition P of, let's see here, so we have ms f plus minus lowercase ms f plus times vs. And the reason I do that is because if you take u of f plus p, that's the sum over all s of ms f plus times vs. And if you take lf plus p, that's the sum over all s of lowercase msf plus times vs. And so you just factor out, you combine like terms because you're using the same partition, and then you factor out the vs and you get this form. and this is going to be less than or equal to the sum over all S in our partition P of, again, uppercase MSF minus lowercase msf times V of S. Okay, and we're going to be using this form. Because really what we want to do is we want to look at MSF plus minus MSF plus and compare it to MSF minus MSF. Because if we have inequality there, then multiplying by the VS is not going to change anything, and summing them is not going to change anything. Okay, so let's prove this. Since F is going to always be less than or equal to F plus, it cannot be that the infimum of F plus is strictly less than the infimum of F, because either F is never negative, in which case F and F plus are exactly the same, or F is negative, in which case MSF will be negative and MSF plus will be 0. So what this means is that, of course, lowercase MSF plus is always going to be greater than or equal to MSF. i.e., if we flip the inequality and put minus signs, we get this. Minus MSF plus is less than or equal to minus MSF. No. Minus MSF plus is less than or equal to minus MSF. Okay, so now if we look at the left and the right hand sides of this inequality that we're trying to prove, we get the minus MSF plus less than or equal to minus MSF. So that part's good. The only thing we need now is capital MSF plus is less than or equal to capital MSF. And this isn't entirely obvious, because we know that F plus is always going to be greater than or equal to F, so why should the supremum of F plus be always less than or equal to the supremum of F? So we also know, like I said, that MS F plus is greater than or equal to MSF. And actually, now that I think about it, I think I might have phrased that in a misleading way. We're not going to prove that MSF plus is less than or equal to MSF. Okay. And so this MSF, capital MSF plus is greater than or equal to capital MSF, because F plus is greater than or equal to MSF. No, because F plus is greater than or equal to F. Okay, so if MSF plus happens to equal MSF, then of course we have MSF plus minus MS. So then we take this inequality that we have from before that says minus lowercase MSF plus is less than or equal to minus lowercase MSF, and we just add capital MSF plus to the left-hand side, and we add capital MSF to the right-hand side, and that doesn't change anything because we're adding the same exact thing to both sides. And so it remains an inequality. So F minus MSF. From which the desired result follows. Because indeed, what this says is that for any S, this inequality holds. So this inequality holds if you sum over all S in this partition P. No, this inequality holds for every single S. And if you multiply this inequality by the volume of S, then the inequality still holds. And then if you sum that over all S in this partition P, then you still have inequality holding. And that's once you sum over all S in the partition P of this thing times the volume of S, that's exactly the inequality that we're trying to prove above. The inequality that's equivalent to UF plus P minus LF plus P less than or equal to UFP minus LFP. Okay, so we're good in the case of MSF plus equals MSF, capital. We still need to consider the case where capital MSF plus is strictly greater than capital MSF. Then, what does this tell us? Okay, so capital MSF plus is strictly greater than capital MSF. So the only difference between F and F plus is that F plus, whenever F is negative, F plus is 0. So what we're saying is happening here is that if we take the max, if we so if we take the maximum of F and 0, or if we take taking the supremum over all f of x is going to give us a strictly smaller number than taking the supremum over all f plus. Now, if f is if f is strictly positive at any point, then f is going to equal f plus at that point, and then f is going to equal f plus at all points in the domain which allow f to take on even greater values. And so if it happens to be the case that f is positive at any point, then the supremum of f has to be equal to the supremum of f plus. And of course, if the supremum of f is 0, then it could be the case that f takes on precisely the value 0 at a point or at some points. But then f plus is going to be 0 everywhere. And so, again, the supremum of f plus will equal the supremum of f. So the only case it could possibly happen that capital MSF plus is strictly greater than capital MSF is if f is strictly less than 0 So I'll write this as there is some negative number r less than 0 such that f at every point is strictly less than r, which is less than 0. So f is not only strictly negative, but it's bounded away from 0. I don't think we really need the fact that it's bounded away from 0. I think all we really need here is that f is negative. But if f was only required to be strictly less than 0, then you could have f getting closer and closer to 0, in which case the supremum of f would be 0. But then the supremum of f would be the same as the supremum of f plus. Okay, so we know that we're only considering the case where f is always a negative function. Okay. So f is always a negative function. This means that f plus is always 0. So ms f plus is going to be capital MS f plus, which is 0. We also know that obviously MSF is going to be strictly less than capital MSF. We don't need strict less. This is going to be less than or equal to. It could be that f is constantly minus 1 or something like that. So what we do, we take What do we do here? Oh, duh. We subtract lowercase msf. So if we subtract lowercase msf from both sides, we get 0 is less than or equal to ms. Here, I'll subtract it, so it's going to be msf minus lowercase msf is going to be greater than or equal to 0. That's just what happens when you subtract lowercase msf from both sides. But now 0 is precisely capital MSF plus minus lowercase msf plus. MSF plus minus MSF plus. And there we go. That's again the inequality that we need. It's just written in the reverse order. So yeah, this is sort of a tricky argument that you have to think through, and it sort of results to thinking in cases. Like, you have to think about, like, okay, so what value could f and f plus possibly be, and what happens in this particular case, and so arguments like this, where you end up considering cases, a lot of times they can be not very elegant arguments. And in fact, if you don't believe in the excluded middle, then you don't allow yourself to consider cases, because considering cases means that, like, okay, so what are the possible scenarios? We have scenario 1, we have scenario 2, we have scenario 3. If scenario 1 is the case, then this happens. If scenario 1 is not true, suppose scenario 2 is true, then this happens. If scenario 2 and 1 are both not true, then we consider scenario 3. Well, you're sort of using the excluded middle and saying that, like, just because these scenarios exist, you're sort of not allowed to say, like, oh, well, if it's not one of these scenarios, then it is this scenario. You're not allowed to do process of elimination. So, I mean, I guess if you're not allowing yourself to use process of elimination, then I'm not too concerned with making sure that my arguments hold for that audience. A lot of times in math, there are a good number of arguments that could be made without using excluded middle, and it's technically better, I suppose, if it's possible to use less equipment to prove something, to not use the equipment. But I still like being able to use excluded middle. I also like being able to use the axiom of choice, so I don't really sweat too much about this. But anyways, the important thing is that we've proven this thing. So there, I'll leave it at the top there. So since f is integrable for all epsilon greater than 0, there exists a partition P such that epsilon is greater than u fp minus l fp. But now we know that this is always going to be greater than or equal to u f plus p minus l f plus p. This is precisely what we just went through all the trouble of trying to prove. So now, for all epsilon, there's a p such that epsilon is greater than this difference of uf plus p minus lf plus p, which means f plus is integrable. Okay, so next, define f minus to be the maximum of minus f and 0 by a similar argument. F minus is integrable. Okay, that I'm not going to do that. I'm not going to prove that this is integrable. That would just be a lot of work. But it's basically going to end up being a very similar argument. All you have to do is you're going to have to adjust like signs and things like that. So yeah, just sort of like a visual of what we're doing. Let's suppose we have a function like this. Suppose this is f. Then f plus is going to look like this. 0 there. F plus is going to look like that. F minus, we're going to have 0, and then that, and that. So that's f minus. No, f minus is going to look like this. Okay, so now observe that the absolute value of f is equal to f plus f minus. And this, there's a number of different ways to see this. One way is to look at this picture. F plus basically takes all the positive values of f and gives you those. What f minus does is it takes all the negative values of f and it makes them positive. So you can see it that way. Another way you can see it is if you consider any point x. If f of x is positive, then f plus of x is f of x, and f minus of x is 0. And if you consider at any point x where f of x is negative, then f plus of x will be 0, and f minus of x will be negative f of x, which will be negative number, and so it will be a positive value, and so it will be the absolute value. Wait a minute, let me check something really quick. Yes, because the domain is R. Okay, yeah, this works. Okay, cool. So yeah. So the absolute value of f is f plus f minus. By exercise 3-3b, sums of integrable functions are themselves integrable, so the absolute value of s is integrable. Alright? Because the absolute value of f is f plus f minus, and f plus is integrable, and f minus is integrable, so you sum them together and you get an integrable function. Alright, so now finally, since f is less than or equal to the absolute value of f, the integral over a of f is less than or equal to the integral over a of absolute value of f, and this is by exercise 3-5. And so what we do now is we just take the absolute value of this. So we take the absolute value of the integral over all a of f, and this is going to be less than or equal to the integral over all a of the absolute value of f. But now if we think about the integral of the absolute value of f, the absolute value of f is always a positive. The absolute value of f takes on positive values always. So if we think about any lower sum or upper sum, we're taking a sum of a bunch of positive values because both capital MSF and capital MS of absolute value of f and lowercase ms of absolute value of f will always be positive. They could be 0, but because absolute value of f will never be negative, these supremums and infimums can never be negative. And so you're taking a sum of a bunch of positive things, and so it will be positive. So any upper or lower sum of the absolute value of f will be positive, and so if you take the supremum of the lower sums or the infimum of the upper sums, however you want to do it, you're taking infimums or supremums of positive numbers, and so you'll get a positive number. So the integral of over a of the absolute value of f is a positive number, so taking its absolute value doesn't change it. So it's just precisely the integral of the absolute value of f. And this shows that the absolute value of the integral is less than or equal to the integral of the absolute value. So again, I guess the important facts here is that if you've got a function that you're not quite sure how to work with, it's nice to break it down into parts that you do know how to work with. And this is exactly what we do. I don't know, we might even do it later on in this section, but this is certainly what you do when you talk about measure theory. The first thing you do is, like in measure theory, you define the Lebesgue integral. You basically define an integral using measure theory. And you start with functions which are only allowed to take on positive values. Well, values which are greater than or equal to 0. You learn how to integrate those. And then you learn how to combine. Then you look at general functions by looking at, you take a real valued function, a function which can be positive or negative, and you break it up into its positive part and its negative part. And then you see if you can integrate the positive part and the negative part separately. And if you can, then you can combine them. And that's how you define an integral for real valued functions. And then when you move on to complex valued functions, you say, okay, so complex valued functions have a real part and an imaginary part. So the real part is just a real valued function, and the imaginary part is just a real valued function. So you try to see if you can integrate either of those separately, and if so, then you can figure out a way to combine them. And so in that case as well, so basically the idea is you start with simpler classes of functions and build up to more complicated classes of functions. And so here, this is sort of what we've done. We've taken a more complicated function, the absolute value of f, and we've broken it up into two simpler functions, which we sort of know how to work with. And so, yeah, this is just, that's generally like the idea behind this exercise, and it allows you to prove this important fact about inequalities and integrals. And so now we are done with the exercise.